Hello, my dear students. My name is teacher Cosme and welcome to your online class. Today, we are going to have yet another chemistry class. But what is the topic today? Reactants and products. Here on the right side of the screen, you can see that when you combine reactants with two or more reactants, you are going to have a new product. And that is what chemistry is all about when you have chemical reactions, which can be expressed in chemical formulas, right? Okay, so as usual, we are going to establish first our objective for the class. The class has the objective to measure the reactants and products in a chemical reaction. So let's watch this chemical reaction that I got from the internet. Okay, the car punches the balloon and you can see flames. You can see the car going through the flames, right? Well, that is a chemical reaction where you can see reactants and probably a product. Okay, so let's go now to our key concepts, shall we? The key concept number one is that in a chemical reaction, the substances that react together are called reactants. And the substances produced are called products. Okay, the first part was pretty straightforward, but the second part was a little repetitive. But still, that is valid and that is totally and absolutely true. Now, the products have different properties from the reactants. As we have said before, as we have stated, you cannot expect the reactants, right, to have the same properties as the resulting products, because this is something new. That is the other characteristic of a chemical reaction. Now, as a chemical reaction takes place, the atoms in the reactants are rearranged to form the products. That is to say, new bonds are formed, right? If you remember, we've said that the chemical bonds, either ionic or covalent, are broken down and new bonds are formed, right? Okay. Then the number of atoms of each element is the same in both the reactants and the products. That is to say that the atoms are not lost or added, right? We don't have new atoms, and the atoms don't disappear either. And this characteristic is called the conservation of atoms, which we will discuss later on today. And also, we have that in all chemical reactions, the total mass of the reactants is equal. It's the same to the total mass of the products. And this is the law of conservation of mass. That is to say that mass is not destroyed. It's only transformed. Okay? So let's get into it, shall we? So the question today is, where do chemical reactions occur? That's a very simple question, but it's very important to know. You may think, right, as an observer, that chemical reactions only take place in the science labs, but they are actually happening all the time in the everyday world. It means everywhere and every time you look around, right? There is non-stop. Chemical reactions happen all the time. Now, when you eat, your body uses chemical reactions to break down your food into energy, right? We've been talking about the photosynthesis, right? The way that plants process water, minerals, sunlight, and carbon dioxide. Well, when you eat, right, your body uses chemical reactions to separate, to split the food into energy. And other examples, as we have seen, include metal rusting, wood burning, batteries producing electricity, for example, in your cell phone, and obviously photosynthesis in plants, a process that is not obvious, right? Because we don't see it, but it still happens in nature. So here we have a chemical reaction, right? Where bubbles go up in the air because some gas is trapped inside. So they just go up in the air. Okay, let's go to the next question. What are reagents, reactants, and products? What's the difference? Okay, this is an important question because we want to know and we need to know the difference. So reactants and reagents are the substances that are used to bring about the chemical reaction. Okay, both are used to bring about the chemical reaction. A reactant is any substance that's consumed or used up during the reaction, right? Sometimes as we said, the molecules change, right? The molecule composition change because of the atomic bonds, right? And the substance that is produced by a chemical reaction is the product. So that is the name after the chemical reaction. It's a product. It's something new. Remember, we always have to have something new, something that we didn't have before. Okay, so for example, in this animated video, we are seeing something new plus the combustion, right? It's nitric acid and the glove also made of nitrile, and the result is combustion. Now, what is the reaction rate? Well, first of all, not all chemical reactions occur at the same time. That means some chemical reactions take place faster and another chemical reactions take place slower. That means that the rate is smaller or the rate can be bigger. Some happen very quickly, for example, explosions, right? That's something very fast. But other reactions take place over a long time. For example, metal rusting. And we saw that a few classes ago, right? Where you need to wait for the metal to rust, especially iron. Now, the speed that the reactants turn into products is called the reaction rates, right? Reaction rate. And rate, we remember that is nothing more than the speed, right? In this case, the speed of the reaction. Now, can you change the rate? Sure. How can you do that? Well, you only have to add energy. For example, a heat or sunlight or electricity. And there are other forms of energy. These are only a few of them. So adding energy to a reaction can increase the reaction rate significantly. Why? Because you are giving energy to the atoms, right? The atoms have more energy to jump to the next atom shell, and thus you are breaking the bond, right? Also, increasing the concentration or pressure of the reactants can speed up the reaction rates. And here we can see in the graph that increasing either the temperature or the concentration or the pressure, either of the three, can have an effect on the rate of reaction. That means that the more temperature, the more concentration, or the more pressure, the rate of the reaction goes up, right? It goes, you have a faster reaction rate, right? Now, like mathematical expressions, chemical reactions are often described with an equation, right? That means we are going to have formulas with the two sides, one formula on the left side and the result, the formula of the product on the right side of the formula. In equations, the names of the reactants appear on the left of the arrow, right? We are going to express the arrow to indicate the reactants, and the names of the products are on the right, okay? That is the products. Now, the chemical reaction in which hydrogen and oxygen are joined together to form water, for example, is expressed with this equation. So we have an equation for water, right? So hydrogen plus oxygen results in water. Water is the product, whereas the hydrogen and the oxygen are the reactants. And here we have a little experiment with water, okay? And if you remember, water is considered as the universal solvent. Okay, then we have that the products of a chemical reaction have different physical and chemical properties from the reactants, okay? Both physical and chemical properties are different. They are not the same. So in the equation that we saw for water, right? Water is liquid at room temperature, but hydrogen and oxygen are not liquid. They are gases when they are at room temperature. That means the normal temperature, not high, not low. And equations for chemical reactions are also written chemical symbols, right? The chemical symbols that you can find on the periodic table, right? Okay, so here we have a change in color if you can see the liquid that is in the container, right? There are two reactants and you can see a color, a change in color. All right, so moving on. In the chemical equation for the synthesis of hydrogen and oxygen, both of which are diatomic, that is, they are formed of two atoms. So you never find hydrogen or oxygen by themselves, right? They always bond 2 by 2. So when you mix them into water, the symbols show that there are two atoms of hydrogen on the reactant side and two atoms of hydrogen on the product side. Okay, so now you have two, and you can see here on the formula, right? However, while there are two atoms of oxygen on the left side, what happens on the other side, on the right side of the arrow? There is only one atom of oxygen and two atoms of hydrogen. So we say that the equation is unbalanced, right? Because the numbers do not add up, okay? So here, for example, we have ice cubes on ice water, right? And well, the temperature is equalized, so to speak, right? Okay, so next, according to the law of conservation of mass, which we are going to illustrate, the number of atoms of each element may be the same of both the reactants and the products. In other words, no atoms can be added or taken away. So it's not like you lose atoms or some atoms just pop up. That doesn't exist. So as a result, a balanced equation is written as you can see here. Two atoms of hydrogen plus one atom, two molecules, right? Two molecules of hydrogen plus a molecule of oxygen results in two molecules of water, right? This equation is balanced. Why? Because there are four atoms of hydrogen and two atoms of oxygen on each side. So the mass of the products is equal to the ones in the reactants. So we can see here on the right the law of the conservation of mass. On the left, you have zinc plus sulfur atoms. They form molecules, but also they have energy, right? So if you see the weighting scale, it's exactly the same. No new atoms have been formed and no atoms have been lost. Now, let's look at another example of a balanced chemical reaction. In this case, we are going to see a metal, a silver. This metal tarnishes when it reacts with tiny amounts of hydrogen sulfide gas in the air. So the products of this reaction are silver sulfide and hydrogen gas. How can we express the equation only in words? Well, we say that silver plus hydrogen sulfide results in silver sulfide plus hydrogen. But the chemical reaction is two atoms of silver plus the hydrogen sulfide results in silver sulfide plus hydrogen. So as you can see, the number and type of each atom are the same on each side. And we are going to see something, the reverse procedure, how you can polish tarnished silver. That's tarnished, that's polished, okay? Tarnished and polished. Okay, before we go on, let me show you a video.
When two hydrogen atoms collide, they join together to make an H2 molecule. We'll show this join as a bond between the atoms. You can also see the unused bonds on the separate hydrogen atoms that haven't collided yet. When another hydrogen atom crashes into the molecule, it doesn't stick because all the bonds inside the molecule are used up. A box full of hydrogen atoms will quickly turn into a box full of H2 molecules. It's similar with oxygen atoms inside a box, except that oxygen makes 2 bonds with other atoms. When they collide, they join to each other twice to form a double bond. A box full of oxygen atoms will quickly turn into a box full of O2 molecules. H2 and O2 molecules will stay that way unless we do something to change them. What if we put one hydrogen molecule and one oxygen molecule in a box together? In reality, a box filled with gases would contain trillions of molecules. But we just want to look at the action of individual ones. What will they do? Well, we know that they will move in straight lines, and they will crash into the walls and bounce off again. But what happens when they collide with each other? Nothing. They just bounce off. Well, that's not surprising because the molecules are using all their bonds and don't have any left over to reach out and join to other atoms. But what if we light the gases with a flame? Whoa! What happened there? The hydrogen and oxygen molecules busted apart into atoms, and then the atoms rejoined to form a different molecule, H2O, and a leftover oxygen atom on its own. Why did the flame make a difference? And why did we get a new substance? We'll replay this and slow it down so we can follow it. Have a close look at the molecules when we bring in the flame. They speed up. That's what heat is. The hotter, the faster. And when these faster molecules crash into the walls, or each other, they bust apart into atoms. Now that the atoms are on their own, they are free to join to other atoms. And they can join with different ones. Here, one of the oxygen atoms has bonded to both of the hydrogen atoms. And because its valency is 2, it has no unused bonds left over. But the other oxygen atom missed out on getting any hydrogens at all, so it's got 2 unused bonds and is on the lookout for other atoms to join to. And we've run out of hydrogen atoms because we only started with 2 and the other oxygen got them both. But we can fix this by putting an extra H2 into the box at the beginning. Let's do that and light this candle. Nice. That was even louder. Now both oxygens have the 2 hydrogen atoms that they need, and we end up with 2 H2O molecules. Water wasn't there before, so a new substance has been made. Not only that, the old substances have disappeared. This rearrangement of atoms to form a new substance is called a chemical reaction. We'll replay this chemical reaction to show 3 snapshots in time as it goes through different stages. At the beginning, there were 2 H2 molecules and 1 O2 molecule. These starting substances are called the reactants. When the flame busted them apart, there were 4 separate hydrogen and 2 separate oxygen atoms. Then each oxygen atom joined with 2 hydrogen atoms to make 2 H2O molecules, which are called the products of the reaction. We'll now show how the old bonds break and the new bonds are made. To do this, we'll use structural formulas which show the molecules as symbols joined by sticks. When the reactant molecules are pulled apart, the bond inside each H2 and the double bond inside the O2 are broken. When the H2O products are formed, 4 new bonds are made inside their molecules. The H2 and O2 have disappeared and are replaced by the H2O. A new substance has been formed, so this qualifies as a chemical reaction. But the molecules in chemical reactions are too small to see, so how can we tell if one's happening? Well, any evidence that shows that a new substance is being made or that an old substance is disappearing indicates that a chemical reaction is going on. Telltale signs include a colour change, a cloudy precipitate forming, bubbles of gas, a new smell, or a solid dissolving. The breaking of old bonds and the forming of new bonds changes the energy inside the molecules too. So heat, light, and noise can also be signs. If the bonds in a reaction release energy, this goes into the surroundings and heats them up. A thermometer shows this as a rising temperature. A reaction that releases energy is called exothermic. If the bonds absorb energy, this is pulled out of the surroundings and cools them down. A thermometer shows a falling temperature instead. A reaction that absorbs energy is called endothermic. Each reaction is unique and has its own combination of signs. Different chemical reactions are happening everywhere all the time. Right now, the bonds of the molecules inside your body are being broken and new bonds are being made. Old substances are disappearing and new substances are being formed. In fact, chemical reactions are keeping you alive.
Okay, so now you know that the reactants and the products have the same number of atoms, and some energy might be either needed or released. Thank you very much for your attention today. Don't forget to ask your questions next time we meet together on the Zoom meeting or any other platform. Bye-bye.